Okay, so today we're going to talk a little bit about work, power, and then relate it back to kinetic and potential energy, how they are related. So work is simply when a force is exerted and causes an object to move in the direction of the force. So those two things have to happen. Force has to be exerted, and the object has to move in the direction of that force. Okay, work is done as long as the force is being applied and movement is occurring. Okay, so for an example here, if we have a bowler throws the ball down the lane. Now, work is being done as long as this bowler is touching the bowling ball. So, as long as the ball is in his hand, okay, he's doing work on the ball. So, the player is doing work on the ball, and then once it releases, no more work is being done. Okay, now if the bowler is just holding the ball in his hand, no work is being done. It has to move, it has to have movement. It has to move, and it has to move in the direction that the force is being applied. Okay, so again, work is only done if the object moves. Okay, and we can calculate work by simply multiplying force times the distance, and the unit for work is joules. So here are two examples. How much work energy is needed to lift an object that weighs, or that weight, so I should say weighs here, 10 newtons to a height of 3 meters. Okay, so the amount of work is force times distance. We need to use a force of 10 newtons. We need to move it 3 meters. So 10 times 3, we get 30 joules of work. Okay. Next one, number 2. How much work is done if a man pushes it on a wall with 30 newtons of force, but the wall doesn't move? So if the wall is not moving, then there is no work done. Yes, we are applying a force. Yes, we are exerting energy. Okay, we are exerting energy, but we are not doing work. Okay, in order for work to be done, there must be movement. There must be movement. Okay, even in chemistry, we do work on things, and it's when the volume changes, and that's essentially a movement. Okay, work is only done when the volume changes. So again, a movement. It's increasing, expanding the volume. So it's always when movement is occurring. All right. Now, also, it has to be the direction of the force has to also be in the direction of the movement. Okay, and this can get a little bit confusing. Okay, so for example, here, if we're pushing a box along the floor, and the box is moving in that direction that we're pushing, then we do have work. Okay, if we're holding a backpack, we're holding up a backpack and we're just standing there, we're holding the backpack up. Okay, just the backpack is staying there, but we're moving forward. There's no force that we're fighting against to move forward. There's nothing we're applying force, yes, but there's nothing resisting our movement. Okay? So there is no work being done here. Okay? If we lift up a bag of groceries, so we take it from the floor, lift it up, the direction of the force is pulling up, the direction of the motion is up. So yes, we have work. Okay, same thing if we're carrying that bag. Okay, we just lifted it, but the motion is moving to the right, then we don't have any work. So again, we have to apply force, and the force has to be in the direction of the motion. Okay. Now, if we increase the force of the object, so if we increase the weight of the object, we're going to increase the amount of work. And most of the time here, when we talk about work, we're going to talk about lifting objects up. We're going to be talking about going against the force of gravity. So pretty much every example that we talk about today and every problem that you're going to be dealing with will be dealing with the force of gravity. Okay, we could deal with the force of friction, but most of the time in this class, we just assume that there is no friction. Okay, so here we're just going to be mostly talking about force of gravity. Okay, so if we're lifting something up, if we increase the force or the weight of the object, so that's the force of gravity of the object, then we'll increase the work. So this one, if we're lifting it from the floor to our waist, and the object weighs 80 newtons, and we're lifting it 1 meter, then we're doing 80 joules of work. If we increase the weight, so we added weight here, 160 newtons, so it's the weight of it is 160 newtons, and we're still raising it 1 meter. Okay, then we double that the amount of work we need to do because we doubled the weight. Okay, now if we have the original weight, but we double the distance lifting it, we're lifting it 2 meters now. Now we have 160 joules of work. Okay, so if we double the weight but keep the distance the same, we should get the same amount of work, or double the work. If we double the distance move, we keep the weight the same, we'll still double the amount of work. If we doubled both of them, we'd quadruple the amount of work, right? We 4 times it, right? So increasing the force or the weight of the object and increasing the distance will increase the amount of work that we have to do to move that object. Okay, now power and work, this is kind of a real quick little thing here. Power is the rate at which work is done. I'm sure you've heard this unit of power before. Power, the unit is watts, and power is just work divided by the time it takes to do that work. Okay, so work is in joules, time is in seconds, so joules per second, and that unit is watts. Okay, really easy example here. We're not going to talk too much about power here, but just a little snippet here. So example, if you do 50 joules of work in 5 seconds, how much power is used? So 50 joules divided by 5 seconds, it's 10 watts of power. So 10 watts of power, joules per second. Okay, now let's talk about work and ramps. So the amount of work needed to lift an object 10 meters is going to be the same regardless of whether you use a ramp or not. Okay, it's always going to be the same. So the force here is going to be, that we're fighting against, is the vertical force of gravity. Okay, what we're ignoring here and why this is a little bit confusing, we're going to ignore the force of friction. So really, this guy's pushing this box, right? He's pushing this box, but he's not fighting friction at all. What he's actually doing is some of his motion is moving in a horizontal direction, but because it's at an incline, some of the force is going in the vertical direction. Okay, so if you have a gently sloping ramp, okay, most of the force is going forward, only a tiny bit of the force is going up. So we actually have the same amount of work being done, but it's going to be less force over a greater distance. Because remember, work is force times distance, right? So here we're actually increasing the distance that we're doing the work. Okay, so we need less force over a longer distance. Okay, you need to do you do a little bit of force at a time, just a little bit by little bit by little bit by little bit. Whereas if you had a steep ramp where you're just trying to lift it up off the ground, okay, the force has to be applied in a very short period of time. It has to be applied in a very short distance. Okay, so you have to apply a lot of force in that same amount of distance. Okay, now if you were to include friction in this, so if you were to include friction, the amount of force or the amount of work would actually increase. However, we're excluding friction. And if you think about it, most of the time when we use a ramp, so a ramp is actually an example of a simple machine. And we're going to talk about simple machines next. Okay, and a ramp is an example of a simple machine. And usually when we use a ramp, we use another simple machine, a wheel. A wheel reduces friction to basically nothing, right? So usually you put this box on a hand truck or a hand cart, and then we can push it along using 2 different simple machines, using that hand truck and a ramp. So these are, again, 2 simple machines. Simple machines usually make work easier. Okay? And most of the time they make work easier by spreading out the force over a greater distance. Okay, so we can do less force over a greater distance, but still do the same amount of work. Okay, and when we have an inclined plane, actually a ramp is called an inclined plane. That's what the kind of simple machine it is. We have something called a mechanical advantage. We'll talk about this when we get to simple machines. But the longer the ramp, the greater mechanical advantage something has. So we can have less force, but over a greater distance. We don't have to apply as much force. And this is a very good concept to understand. Also, just keep in mind that the friction is being neglected here. The friction of the ramp is being neglected here. All right, as we get a more and more flattened ramp, the friction becomes greater and greater. Okay, but we're not going to worry about that. We're just going to assume that there is no friction here. All right. Now let's talk about ramps and velocity. So if we have a ramp that has a steep angle, like this diagram B here, compared to one that doesn't have as much of a steep angle, so less steep, but the distance fallen, the vertical distance fallen is the same. Okay, it doesn't matter what the ramp angle is, as long as the distance fallen is the same and there is no friction, the final velocities of these two objects will be the same. Okay, so regardless of whether you dropped it straight down, whether you drop it at an angle slowly, like or at a big angle or at a less of an angle, the final velocity will always be the same. Okay, and this again has to, when we're talking about this, we're talking about no friction. Okay, there's no friction here. Okay, if there was friction, this would be a different story, and the the less inclined ramp would probably have a slower velocity in the end because there would be more friction force. But we're assuming no friction. Okay, no friction. The only force acting upon this is gravity. Okay, the only force acting upon this is gravity, so the vertical distance fallen will be the same. Therefore, the final velocity will be the same. And we can find the final velocity by comparing potential energy at the top and kinetic energy at the bottom. Potential energy at the top is mass times gravity times height. And the kinetic energy at the bottom is 1/2 mv squared. So the mgh should equal 1/2 mv squared. If you set those two things equal to each other, you'll actually see that mass does not matter. Okay, mass does not matter. And let me show you that. So if we look at, again, kinetic energy is 1/2 mv squared, and potential energy is mgh. Okay, like I said, as we start at the top, we have all potential energy, right? At the top of the ramp, we have all potential energy, right? And then it's all converted into kinetic energy. So by the time we get to the bottom, it's all kinetic energy, okay? And this potential energy is totally based on the height. Same thing here. Potential energy, all converted to kinetic energy, and the vertical distance is the same. So the potential energy here and the kinetic energy here are equal, and they're equal over here as well. Okay, if we want to find the velocity, the final velocity, what we can do is we can say 1/2 mv squared equals mgh. Okay, and you'll see actually you have m on this side and m on this side. You can actually cancel them out. All right, if we want to solve for velocity here, we multiply both sides by 2, multiply by 2, and square it. So the velocity is actually equal to the square root of gh times 2. So 2gh, square root of 2gh. Velocity equals square root of 2gh. Okay, so the final velocity is only dependent on the height at which something is dropped. Okay, and there's two reasons for this. One, there's no friction. We're ignoring friction. And number two, we're ignoring air resistance, which is the same thing as friction. Okay, no air resistance and no friction. Because there's no air resistance and no friction, the velocity of any object falling from a height, doesn't matter if it's a ramp or if it's straight down, is the square root of 2gh. Okay, and again, we derive that from these setting ke equal to pe. Okay. So with everything there, you should be able to complete this worksheet that I have assigned you for today. Okay, do your best on that, and I will see you all tomorrow.